So the graph here is a view on the left-hand side of Kleiber's data, with the horizontal axis here being body weight in kilograms, and the vertical axis being calories consumed, C, and I've rescaled them on this particular set of axes to be in megacalories. So that's just the calories that were in your table divided by 1,000 to get the vertical axis. So these are the actual data points on the left. On the right-hand side is plotted the logs. So this is the log of C, sorry, log of W versus the log of C. And you'll notice, of course, that the data on the right-hand side in the transformed plot is exactly linear. There's a linear equation running through them. The slope is about 3/4. It's that same 3/4 that you saw on the exam question. So groups that worked on question L3, what I asked you to do was to take the data that you were given in your data table and determine, using the symmetric differencing method, the average rates of change at each point. When you found these values of delta C over delta W, you were really finding the slopes of some lines that connect 2 points on this graph. The 19.2 number that you found was the slope of the line segment joining the point at W equals 40 to the point at W equals 60. And then you assigned that slope to the point 50. So 19.2 was the slope of that line. Then at the next point, we went from 50 to 70, got the slope of that line, and then assigned that slope to a mass of 60 kilograms, and that was 18.35. And then after that, you found the slope joining the next pair of points, 60 and 80, and you assigned that slope to W equals 70, and that slope was 17.65. And last but not least, connecting 70 to 90, you had that slope, and you assigned that slope, which was 17.05, to the mass 80 kilograms, 17.05. So first of all, let's pick on one of these numbers. This was part C of the question, where we pick on this number 18.35. And I want to know, what is that number 18.35 telling us about the relationship between body mass and calorie consumption? So this 18.35 means what? How do we turn that slope into a sentence?
Well, we had for our answer that a human would burn 18.35 kilocalories per kilogram when the mass of the human is 60 kilograms.
18.35 kilocalories per kilogram if the mass of that human is 60 kilograms. So maybe you write it like this. A 60 kilogram human burns 18.35 kilocalories per kilogram. So then one thing I want to add to this sentence. This is something I added to several of your explanations of slope on the exam. Keep in mind that any slope is a rate of change. And if we just put a 60 kilogram human burns 18.35 kilocalories per kilogram, as it's written, it sounds like that this human should be burning a total of 18.35 times 60. Let's find what that is for a second here. 18.35 times 60, 1,101 kilocalories. And yet, that's not what's shown in the data. In the data, the 60 kilogram human was burning 1,466 kilocalories. So we need something to make this sentence a little bit more accurate. What do I need here? Well, average, but it's an average between 50 and 70 kilograms. I'm looking at a different word here, another different word that starts with A. It's a word I added to a lot of your slopes on the exam. Additional. So a 60 kilogram human is going to burn 18.35 additional kilocalories for every what? For every additional 1 kilogram gained. So if my mass is 60 kilograms, it's not. I don't think it ever was, since I was probably 9. But if my mass were 60 kilograms, and I gain a kilogram, so I put on a kilogram of weight, that means that my body is now going to burn 18.35 more calories per day. If I start at 60 kilograms. So remember, a slope is a statement about change. It's a statement about additional, rather than a statement about absolute numbers. So as it was originally written, if a 60 kilogram human burns 18.35 kilocalories per every kilogram that human has, that makes it sound like an average rate of change from 0 to 60, which is not what we want. Instead, here we had an average rate of change from 50 to 70, which was intended to approximate the instantaneous rate of change at 60. So a 60 kilogram human, for every additional kilogram that human gains, starting from 60, they're going to increase their metabolic rate at a rate of 18.35 kilocalories per kilogram. So again, that word additional is really important to an accurate interpretation of what these rates of change mean. We want to know in Part D, what does it mean? In other words, what is it telling us, the fact that the rate of change when W equals 80, that's this number up here, 17.05, is smaller than the rate of change at W equals 50, 19.2. So this is bigger than this rate of change. So what's that telling us? How could you write a sentence to interpret for the New York Times what this is telling you? What would this tell the average dieter, let's say? What does this mean? That our rates of change are getting smaller as your mass gets bigger. What did you write for a sentence?
We actually wrote less kilocalories per kilogram are burned when we have a larger mass.
Okay.
I guess it should actually be less additional kilocalories per additional kilogram per gram.
Okay. Yeah, that's a good modification. So humans that have a larger mass, so a person who weighs more, if we're all subject to the same gravity, larger mass means larger weight. So humans with a larger mass will burn fewer, how'd you say it, fewer additional?
Yeah, less additional kilocalories.
Right. Per each additional kilogram of mass gained. Right? So if I'm an elite gymnast or something, which I'm definitely not, but if I were an elite gymnast and I had a mass of 50 kilograms or something like that, that's probably large for an elite gymnast. But if I'm really, really small and I gain 1 kilogram, then my metabolism is going to go up by a fairly large amount. Right? Whereas if I'm me, generally a couch dweller on most days, if I have a larger mass and I gain an additional kilogram, my metabolism is also going to go up, but it's not going to go up by as much as the gymnasts went up in gaining that kilogram. So the rate at which your metabolism increases as you gain weight, that rate slows down, which is a little disappointing to think about it in terms of gaining weight sometimes. We could also think about it in terms of losing. Instead of adding, instead of gaining, we could also turn this around and make it a statement about losing mass. So for every kilogram lost, I'm going to burn, well, more, I guess, additional calories. In other words, in order to lose 1 more kilogram, I need to, if I start out at 90 kilograms, I need to cut 17 calories out of my diet daily in order to lose a kilogram, in order to get down to the metabolism that a 89 kilogram person would have. But as I lose mass, the number of calories that I need to cut out in order to lose 1 more kilogram gets bigger and bigger. Anyone who's ever done any extended dieting will know that there's diminishing returns after a while, that cutting a certain number of calories out of your diet works really well in the beginning, but then it gets harder and harder as your mass goes down. So that's what the shape of this curve and the behavior of these rates of change are telling us. And it's hard to detect from this graph itself, because even at the scale that we're looking at right here, this graph looks kind of like a straight line, even on the nonlinear, even on the original axes. By the way, we didn't have to do any fancy interpretation with the log scales or anything, because our axes here were the original axes, W and C. So we didn't have to do the sleight of hand that you did on the quiz. But if we were to exaggerate the shape of the graph we're looking at on the left, the shape of the graph actually looks something more like, it bends a little bit. Maybe you can tell in this graph, which direction is it bending? Graph on the left. Outward? Like this? Yeah. If we exaggerate the shape of the graph, it looks like that. And it's an example of what we call in calculus a graph which is concave down. Concave down would mean that, if, let's say that we had rain coming down on top of this graph, the rain would roll off instead of collecting, right? It's like an upside down bowl and not a right side up bowl. It's concave down, and concave down in calculus is going to mean that the rates of change decrease, as in the example we just looked at.